Okay, so well, before we begin, let me just say a few things. Your midterm grades have been posted to CCLE. Okay, for some reason they're not showing up in my UCLA, and sometimes things like I always put my grades up in CCLE, and sometimes they appear in my UCLA, and sometimes they don't. So just check CCLE. There's a grade book area at CCLE. You can see your grade there. You'll see your raw score. The raw score is how many, there were 100 points possible on the exam, and the raw score is how many points you earned. And then the score that appears in the grade book is what I call a scaled score. I don't like to use the word curve, because curve generally implies that a certain number will get A's and a certain number will get B's and a certain number will get C's or things like that. And I don't like to choose cutoff points and break points that way. The way I choose to adjust grades at the end is I kind of look at the overall class performance as a whole. I usually look at the median, and I try to make adjustments to the median accordingly. And so after the scaling factor, the median scores an 83, okay? And Q3, so the 75th percentile is around a 90, and Q1 is around a 70, okay? The scaling factor is you take your raw score, you multiply it by 0.8, so 80% of your raw score plus 27 points, okay? So that's how the scaling was done, and that should be that. If you I will give the exams back to the TAs to return during section, so you can pick up your exam then. And if you miss it, you can come by office hours. If you have any questions about the exam, you can come see me. Pretty much once you have the exam, you can just type in the code into R and see exactly how R behaves. And if you have questions about why a certain thing works a certain way, feel free to ask me. What else do I need to say? Yeah, I guess, okay. And then, like I always say, it's just one exam in one class, and has no bearing on who you are. And I look forward to the day where students are not so consumed by grading, okay? And I know, it feels odd to say, especially because, the university requires me to grade you guys and give scores to you, but I hope you don't evaluate your education based on how well you performed in a class, but rather what you learned. And I know we like getting good grades, but your opinions about a course should not be dependent upon the grade you earn. It should be about, I think, the content that you took away with. I hope you feel like you're learning stuff in this class. I know the homework assignments are challenging, but I also hope they are instructional, in that by forcing you guys through these tough exercises, you come away feeling like you can tackle additional challenges or projects in the future, okay? Rather than, I try to avoid doing too many textbook problems that don't have a ton of practical value in terms of what you might be required to do in the real world and things like that. Although, today our course takes a little bit of a thematic shift here. So, okay. And if you have any feedback, if you have any comments or concerns, please approach me during office hours, or approach me and let me know. I'm always looking to try to improve the class for future students and things like that. One of the comments I got back was the exam felt a little bit too long, so I'll take that into mind. I tried to take that into mind when I did the scaling factor as well, and I'll try to take that into mind, as far as future exams go. But any other feedback you have, I welcome it. So please let me know. Again, what I don't want is I don't want you guys to just, if you're upset about something, I don't want you to just keep it to yourself and then take it out during the course evaluation at the end of the quarter, okay? Because as for me, this is my third year teaching here at UCLA, and so I'm still considered new and in this kind of probationary period, and so your course evaluations do mean a lot for me in the future of my career. So I'm trying to do my best in terms of getting your feedback and making the class what you want it to be, and the balance between what you want it to be and what I feel is necessary to be covered. So again, don't just take all your rage out on me during the course evaluation or on Brew and Walk or whatever it might be. Okay. Okay. So today, on Monday, we wrapped up ggplot, and that kind of wraps up the intermediate programming. And so what we do today, starting today, there is a bit of a thematic shift in the course content. Some students have commented or maybe complained that it feels like it's two courses in one, and I would agree that is part of it by design. And so today we are going to start covering the computational statistics part. Okay, so before was kind of just learning the intermediate programming so that when you are faced with a task, you can accomplish the programming aspect in R. And today we will cover, or we're going to start to cover some of the numeric aspects as far as doing statistics, answering statistical questions with the computer. Okay, and before we can get into stuff like that, so one of the big things is going to be like root finding methods and optimization methods, and before we can really get into that, we need to have an understanding of numbers in the computer. Okay, because a lot of times it feels like when you are multiplying numbers and you're doing arithmetic operations on the computer, it feels like you're just doing arithmetic like in real life, okay? You ask the computer, what's 5 times 7? And the computer says 35, and it feels very normal and comfortable. However, there is a very, very, very important distinction, okay? In that, with real numbers, okay, how many real numbers are there? Infinity, right? There's an infinite number of numbers, right? Infinite numbers, okay? And how many real numbers exist between 1 and 10? Infinity, right? How many numbers exist between 10 and 10.1? Infinity, right? So with real numbers, we have an infinite number of numbers between any interval that we can specify in the real number line. That is not possible with a computer, right? Because with a computer, you have finite storage space and finite memory, right? So they're like, the value of pi goes on for an infinite number of digits, and and you can't store an infinite number of digits in your computer in any representation, right? And so on the computer, we dedicate in type double, okay, so floating point numbers, which is type double, okay, we use 64 bits to represent a number. Okay, and the 64 bits, this is an attempt to, okay, so what is this? 2 to the 64 is the total number of distinct values that can be represented, right? So at best, we can represent 2 to the 64 distinct values. And 2 to the 64, it's a big number, but it's certainly very short of an infinity, okay? And so, this is what we're going to try to do. We're trying to do our best to represent as much of the number line as possible using 64 bits, okay? And so because of that, we cannot represent every single number. We cannot, it is not possible to represent all the numbers. And so the numbers behave different from what we might expect, okay? So because with the real number line, there's an infinite number of numbers, and you can represent any number or any quantity that you need to. But with floating point numbers, you only have 2 to the 64, at most 2 to the 64 distinct values that can be represented. And because of that, the math does not behave necessarily the way we might expect, okay? Okay, so let me that's all right, so what would happen? Oh, let me fit this into the screen. All right, this is not a trick question. All right, if I type in 0.1 plus 0.2, what will our output? 0.3, right? Okay, so I'm going to say, I'm going to take this, and I will store it into A. Okay, so what is A? A is 0.3. Okay, all right, and so now I do a test. I'm going to do, is A equal to 0.3, and what will this return? It returns false, okay? Which is, you're like, what? What if I did 0.3, is that equal to 0.3? This is true, and I ask, well, what's A? A is 0.3, and I say, is A equal to 0.3? And it says false, okay? This is very confusing, and it feels like, is R broken? Is something wrong, okay? I mean, you could try it out on your computer, and it'll do the same thing, okay? All right, this is what's going on, okay? And I'm going to do, so it's doing this in binary, okay? So underneath the computer, this is happening in binary, okay? And so let me just change something and do options, digits equals 0, can I do 17? Okay, so if I do 0.1 and 17 digits, it's actually not 0.1. It's very close to 0.1, but it's the number 0.1 doesn't actually exist in floating point representation. It doesn't exist out of the 2 to the 64 values that we can represent. 0.1 exactly is not one of them. We have something that's very close, but 0.1 is not one of them. Okay, 0.2 is also not one of the exact values that we can represent. We can represent something close to it, but not exactly. And so if I do 0.1 plus 0.2, okay, I get this. I get 0.3, blah, 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 and it ends with a 4 if I do keep it out to digits equals 17, okay? And okay, and if I ask what is 0.3, we see that it is different, okay? So again, 0.3 cannot be represented exactly in the computer. It gets represented with something very close to it, 0.299999999, but it's not exactly the same, okay? All right, it's kind of like, okay, just imagine, so this is kind of the analogy. Imagine you're trying to keep track of numbers, okay? And you are allowed only 5 digits, okay? So you are allowed 5 digits to represent numbers. Okay. And so somebody says, okay, what is 10 divided by 3? Okay, and you would say, okay, so you have to represent this in digits. You would say 3.3333. This is what you have. This is your 5-digit representation of what 10 divided by 3 is. Okay, and someone says, okay, let us store this as A. Okay, all right, and then we say, okay, what is A plus A plus A? All right, so we would have 3.3333, and we would add all of these things up. And what is the value we would get? We would get 9.9999. Okay, so the question is this equal to 10? And they are not equal, right? Okay, and that's basically what's happening inside the computer, except just in binary. We are not able, in binary, we cannot represent certain values. Just like in decimal, we are not able to represent quantities like 10 divided by 3 exactly in decimal form if we are limited to a finite number of digits. Okay, so the only way to represent 10 over 3 in decimal form is to have an infinite number of digits, which is not possible. Okay, you might say, okay, I can store 1,000 digits or something. Okay, but even at 1,000 digits, if we keep it out to 1,000 digits of precision, you'd have 9 followed by 999 nines, which is still not exactly 10. And so you might say, okay, well, I'm going to do A is equal to 10 divided by 3, and then you do A times 3, and you ask, is it equal to 10? And it's going to return back false, right? And this feels uncomfortable to us, but I think it kind of makes sense what's going on, right? Because we can't represent things, right? And for the computer, 10 over 3 is represented this way. And if I did, I don't know, if I said 3,033,332 divided by 1, 2, 3, 4, 5, 10 to the 5th, okay? This will also be exactly 3.333 in the computer because we're only allowed 5 digits, right? As far as this actually is technically not even allowed to be represented in the computer. Right? So actually, if we're only allowed 5 digits, this number that's 6 digits long is not even allowed. It's either going to be 333330, or and then the next value that we can represent will be 333340. Okay, because if you're only allowed 5 significant digits, these are the only things that would be allowed. Okay, so at a high level, does this make sense? What's going on? Okay, and so so yeah, your computer R behaves a little bit funny, right? So how do you say is A? So again, A equal to 0.3 is going to be false. What option we have is all equal. All equals can be used for vectors, and all equal also basically says, if it's the same up to a certain number of digits, we'll say it's equal. Okay, so it says it's true here. Okay, so all equal only checks for a certain amount of precision here. Tests if 2 objects are nearly equal. Okay, is what all equal does. And you can specify the tolerance it deals with it's the square root of the what we call machine epsilon, which we'll discuss here. Oh no. Hope that's okay. No. All right. All right. Okay, so let's talk floating point precision. I'm going to and this we are going to use the IEEE 754 standard. I think this standard has since been updated. I think I'm looking at the 1984 revision, and they had a more recent revision, which is similar but ever so slightly different. But it still gives us, I think, a decent understanding of what's happening. Okay, so basically, all values are represented in binary. All right, so if you have something like this, then each of these, it starts off with 2 to the 0, 2 to the 1, and 2 squared. So you have 1 times 4 plus 0 times 2 plus 1 times 1, and that's going to be equal to 5. So 101 is 5, and there you have that, okay? If we need to represent fractional numbers, fractional binary numbers, then you'll have 101 and then a point that we would call this a binary point, not a decimal point. And then maybe we would have 1 and 1, okay? So right here, this is 2 to the 0. This one is 2 to the 1, and over here is 2 to the 2. So this part is still 4 plus 0 plus 1, okay? And then this position right here is going to be 2 to the negative 1. So this is equal to 1/2. And this is 2 to the negative 2. So this is equal to 1/4. So this value gets represented. This is going to be 5.75 or 5 3/4. Okay. Is that okay? So to illustrate our examples in class, we will deal with what we call a mini float number. Okay. So for illustration, we will have a mini float. Okay. So a real type double uses 64 bits. Here we will use 8 bits. 8 bits to represent our values. Okay, and we split up the 8 bits into 3 groups. Okay, one is for the sign, positive 0 for positive, 1 for negative. Okay, 3 bits are for the exponent. And the 4 bits are for what we call the mantissa. Mantissa, or some places call it the significand. Okay. And so we would use let me just check my notes here. Okay, and all right, so I'm going to just write our 8 bits here. Okay, and we might put something like 0, and then we'll have this is our exponent. So this is our sine, our exponent, and our mantissa. Okay, and basically we will use our 8 bits to represent numbers in scientific notation. Okay, so we use our bits and so so let's say we wanted to represent the number 0.575 in binary. Okay. All right. So the way this would work is first we would go. We would think, what does this look like in actually, this is not a good example. I'm sorry. Let's just start off with 0.5, okay? So we'll start off with 0.5, okay? So this is our decimal value, okay? What is this in binary? This would just be 0.1, right? In binary, because the first place after the decimal is the halves place. So we would represent 0.5 in decimal as 0.1 in binary. Okay, and then if we wanted to make this binary scientific notation, okay, how does scientific notation work? The leading number has to be something other than 0, right? So this would be 1.0 times, and what would we multiply this by? So it's in binary scientific, so it's not going to be multiplied by a power of 10, but going to be multiplied by a power of 2. And what is that power that we multiply it by? 2 to the negative 1. Okay? Is that okay? And if, let's say I had something like 0.25, okay, as decimal. So in binary, what would this be? 0.01, right? This is kind of the quarter place. So in binary scientific, I would have 1.0 times 2 to the negative 2. Okay, so in binary scientific, you've got kind of this part we would call the mantissa, or the significand, times 2 to the, and then this part is the exponent. This is okay? All right, so I've got 3 bits for the exponent, So how many values can I represent with my exponent? So in the mini float, I have 3 bits for the exponent. Okay, so I can represent a total of 8 values. Okay, and those 8 unique values, the 8 values are going to be in binary 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, those are the 8 values I can represent. With my exponent, I want to be able to represent both positive and negative numbers. Okay? So what should I do? What I'm going to do is, rather than saying this number, which traditionally we would say is 0, and this one is 7, if I said this is 0, 1, 2, 3, like we normally do for binary, then I can only represent positive numbers with my exponent, right? So what we do is we use what's called the biased scheme, and basically we just shift where 0 is, okay? So the biased scheme shifts where 0 is, okay? And so what we do is we end up putting this here as 0. So this becomes 0. And then I go 1, 2, 3. I can represent an exponent as big as 4 and as low as -3. Okay? And so because we shifted 0 over 3 spaces, the bias here, the bias is equal to 3. Okay? And by using bias, I can represent both positive and negative values without the need to designate 1 bit to be the sign. Okay? Because another option would have been saying, like, I've got 3 bits for the exponent. The first bit will be the sign, and the other 2 bits will be the number. Okay? What's the disadvantage there? The disadvantage with that, and the reason why we don't do it, is because we're going to end up with both positive 0 and negative 0. Okay? And so one of those values is entirely redundant, right? So it's almost a waste. And so in order to kind of maximize, so we would have a total of 7 unique values. We could go to positive 3, negative 3, and we would have 0. Okay, so to kind of maximize the number of values we can represent, we want to be able to represent 8 different values. We use a biased scheme, and we say we're going to have only 1 0, but it's going to be shifted somewhere. Okay, and here we shifted it over 3 spots, so here our bias is 3. Does that kind of make sense? What's happening here? All right, and so in general, if you have n bits, n bits in the exponent, okay, the bias is 2 raised to the n minus 1 minus 1. Okay, so in this case we've got 3 bits. So we have 2 raised to the 3 minus 1. So 2 squared is 4 minus 1 gives me 3. So this is how we represent numbers here, okay? Is this okay as far as representing the exponent? Okay. And then, so now I have 4 bits for the mantissa. And so I've got 1, 2, 3, 4. And remember, these are going to be the bits for binary scientific notation. And in binary scientific notation, the leading digit should be anything but a 0, right? So if we're binary, the leading digit will have to be a 1. Okay? It can't be a 2 or a 3 or anything like that because you can only have 0s and 1s. And so in binary, the leading digit will be a 1. Okay? And if we assume it's always going to be scientific notation, then there's no need to encode that. We don't need to say the leading digit is a 1. That's going to be understood. And so these 4 bits can be used for just the 4 bits that come directly after the binary point, like the decimal point, but binary, okay? So if we assume it is always scientific, it is always in scientific notation, we know the leading digit cannot be a 0 and it must be a 1. Okay. And so here, if let's say I've got, so here's my sine and my exponent, 1, 2, 3, and my mantissa is 1, 2, 3, 4. Okay. Let's say I have, I'm going to put in 0, 1, 0, 1, 0, 1, 1, 1. Okay. So let's say this is how the number is stored. Okay. What does this number represent? Okay. Well, we know it's going to be positive. And then the significand, the mantissa, will be, we know the leading digit has to be a 1, and then we just copy the 0, 1, 1 over. 0, 1, 1, 1 over. And then we multiply this times 2 to the, and then we're going to have to do the exponent. Okay. So we can kind of flip back and we can ask, flip back to the previous slide, and what number does 101 correspond to on the previous slide? And I think it's 2. Okay. Or we can say, all right, well, 101 is equal to 6, right, in binary. It's equal to 5 in binary. So 4 plus 1 is 5. But then you subtract off the bias of 3, and so this value represents 2. Okay, 2 raised to the exponent. So you can say if the exponent is equal to 101, then that translates from binary into decimal into 5. Our bias is 3, therefore 5 minus 3 is 2. So this value is 1.0111 times 2 to the 2. Is that okay? All right, and so what is 1.0111 times 2 to the 2? Okay, we have a couple ways to do this. One is you can just move this decimal over, or not decimal, binary point over 2 positions, because we were raised 2 to the 2, and we would have 101.11, and I think this is easy or I hope we recognize this. Okay, so 101, this is going to be 5 point, and then the decimal here, or the value behind the first binary is 1, so that's plus a half, and another 1, so that's plus a quarter, so this is going to be 5.75. Okay. You could do this the alternate way. So I've got 1.0111 times 2 to the negative 2. You could also say, well, this is 1.1 plus 0 halves plus 1/4 plus 1/8 plus 1/16, right? This entire thing times 2 to the 2 times 4. And so you would get 4 plus 1 plus 1/8 times 4 is 1/2. And 1/16 times 4 is 1/4, and you would also get the same thing, 5.75. Okay, so either way you want to do it, you can move the binary point over, or you can go directly to converting it into fractions and then multiplying it by the exponent. All right. Yes. Question.
Is that -2 on the top potential?
I'm sorry. Yeah. That should be +2. +2. I apologize. Okay. Okay. We'll continue on Friday. But this is just to kind of introduce the topic of floating points and to recognize that floating point math is different from real valued math.